Hi guys, today we're going to continue our journey into basic electronics, and we're going to talk about another type of component, which is the diode. I have two diodes here. You can see this one is like a little glass enclosure, okay, with two wires and a marking on one end. This one is similar. This is made of plastic. You can see this has a part number printed on it, letters and numbers, and again a little line at one end, different colour. And we also have bad boys like this one, so this is much larger, part number again 6A10. It's like a big brother to that one really. And we have one more, and this one you will see has a part number and a funny symbol on it. So these are all diodes. Now the fact that one end is marked on these and we have a symbol on this one should tell you one important factor, and that is that the diode is polarized. The two ends are different, and this is why they mark, so we know effectively which end is which. So let's have a look to see what diodes do. We can have a little bit of fun with this today. We will prove a few things about them, and I'm sure at the end you'll have a good understanding. As we've just seen, the diodes have two connections, two leads, and they are marked so that we know one end from the other. We know which way round the diode is. And that's because the diode has a special property. It's important to know which end is which. And that property is to pass current only in one direction. So we had diodes that looked like this, with a stripe on one end of it. And we also had another one which had a symbol on it like this. This is actually the schematic symbol for a diode. Now there are a number of types of diodes. There are some specialist diodes, but we won't go into those in this video. We're just going to talk about diodes in this one, and the next one we'll talk about some of the various different types, the variations we get, and why. This symbol is actually very useful because it tells us the direction in which current flows. So from the symbol, effectively we have an arrow with a line, and the current flows, talking in conventional current, which is positive to negative, in this direction, plus to minus. This direction is the direction of the arrow in the symbol, so we can easily see and memorize that is the direction the current flows. You'll notice that the diodes which had a coloured bar at one end, this equates to this line on the symbol, so the current also flows in that direction. You can imagine the diode was like that. Yeah. So the black bar or coloured bar on the packaging represents this bar. And these two ends of the diode have names, which is not surprising really. This end is called the anode, and this end is called the cathode. Sometimes you will see these abbreviated on the printing on the PCB. Don't be surprised to see cathode abbreviated as a letter K rather than a letter C. That's because it's just from a different language originally, okay? So you'll see that sometimes actually marked on the PCBs, AK, AC. K is the same as C. It's just a cath with a K. You know I like to talk about water on these videos, the water analogy. So let's have a water analogy for our diodes. So we can imagine we have a water pipe which comes to a wider section like so. And here is a valve that can block the opening. And on this, it has a little spring attached like so. So when water flows in this direction, high pressure to low pressure, positive to negative, the water pushes on this little flap, and the force of the water counteracts the force of the spring, which is holding this closed. So the little valve actually opens, like so, and lets water pass through. Okay, water passes through. But when you try to pass water the other way through this pipe, this way, the force of the water actually just holds this valve against this section, so it can't move that way. In fact, you're just reinforcing the pressure holding the valve shut that the spring is giving. So you can see that water can't pass that way, but it can pass this way. Now, if you want, you can go and look up the science of how the diode actually works. Personally, I think for the point of electronics, if you're a hobbyist or a repair technician, you don't need to know exactly what's going on inside the diode. You just need to know that this is what it does and that it works. So if you want to go look up all the science of electrons and holes and stuff like, get over there and do it, but you won't be hearing it from me. So we can draw a graph, because graphs are fun, yeah? Graphs are better than maths. So we'll have a graph. This represents the current, I, current. Okay, higher, lower. This is voltage, positive, negative. Volts. So we know in the negative direction the diode doesn't conduct. So as the voltage increases, the current is 0. And in the other direction, once we apply some voltage, the current basically is infinite. It's a short circuit. But remember, from our little diagram, we have a spring here. So we should realise that we have to apply some pressure of water to counteract the force that's holding this valve shut, the force of the spring. So I think it's reasonable to understand that our diode will not be perfect like this. We have to put some pressure on before that opens, which in the terms of electronics means we have to apply some voltage in this direction before it will conduct. Hey, my white pen doesn't work very well on my white paper. Let's do that again. So we have to apply some voltage in the forward direction before the diode will effectively switch on and conduct. So we can prove this. We can take a power supply, we can connect it to our diode, and we can monitor the current. We can use the power supply to do that. And let's just prove, so that we know that the diode does in fact only pass current in one direction. Here we have a power supply. This is a variable power supply. It's set to 12 volts. So if we apply 12 volts to our diode with a negative to here and the positive to here, according to the theory we just looked at, this diode shouldn't conduct. So nothing happens. This is the current is 0. If we apply the current the other way, the diode should conduct. How much current will flow? Well, the power supply can only supply 5 amps. If it tries to supply more than 5 amps, then the voltage here just comes down to 0. So let's see how much current will flow through our diode. Well, quite a lot. Is something happening? Ah! Something is happening. So our diode doesn't like passing 5 amps. Why did our diode smoke? Why did it effectively burn up? Well, the reason is that the diode cannot handle the current that was flowing through it. The only thing limiting the current to 5 amps was the power supply itself will not deliver more than 5 amps. It has a protection built into it that stops it delivering more power than that. So one of the ratings for a diode will specify how much current it can actually pass without failing. And you will not be surprised to know that the larger diodes like these can pass more current. That's why it is physically larger. So that's one of the ratings we will find that make one diode different from another. Now let's have a look to see if the diode actually acts as a short circuit when it's passing current and an open circuit in the other direction. So to do this, we need to limit the current that's flowing through the diode, and I'm going to do that by putting a resistor in series with it. Okay, so I've added a resistor to our circuit. This is a 470 ohm resistor, and we can work out what current will flow through the circuit now. Remember, we did Ohm's law in the previous lesson, so let's use it. So we know that we're going to apply 12 volts to the circuit, and Ohm's law tells us that the current is the voltage 12 divided by the resistance, which is 470 ohms. So 12 volts divided by 470 ohms, 0.025 amps. That's 25 milliamps. Also, we can work out, because we did this in the previous lesson, the wattage dissipated on this is the current, which is that, times the voltage, 12, which is 0.3 of a watt. This resistor is a 1 watt resistor, so this will not burn up, it may get warm. So let's apply the current to our diode now and see whether in fact this does act as a short circuit in one direction and open in the other. Well, once again we can apply power, so we'll put the power on, the voltage in the reverse direction, negative to positive, and we know that the diode will not conduct, so there's no current flowing. We can see that there. If we connect it the other way, we've calculated we should see about 25 milliamps. This only reads to a resolution of 10 milliamps, so we might see 0.2 or 0.3. And we see 0.2. It just doesn't have the other digit to show the single milliamps. So the question is whether our diode is actually acting as a short. If it's acting as a short, then there should be no voltage across the diode. A short will drop no volts. So let's have a look to see if there's any voltage across our diode. So we'll connect across the diode, and we can see we have about 0.735, not about exactly, 0.735 volts across the diode. So that is not a short. If it was a short, and we can prove this, because we can short out the diode. I'll clip it on here, easier. Okay, so we're now shorting out the diode. If we measure again, well, we can see the reading is basically 0. So why do we get 0.73 volts across our diode? Well, the reason is very easily demonstrated with our water analogy of water flowing in and out past this valve. The valve is held closed by a spring, and this spring has some tension, so for the valve to open, the spring has to stretch that way. and that requires some pressure to do it. So with our pipe here, we need to put a certain amount of water pressure on here to counteract the force of the spring holding the valve closed. And once we reach that point, the spring, which is still here, will move and allow the water to flow. And as we reduce the water pressure, we will reach a point where the pressure is so low that the spring can pull the valve closed again. And that's what's happening electrically with our diode. We said with a perfect diode, in the reverse direction it won't conduct at all, and in the forward direction it will conduct like a short circuit unless we use something else, the resistor, to limit the current that flows through it. But to get past the pressure of that spring, we have to put some voltage, and at a certain point there's enough voltage for the diode to switch on, and that will just act like a short. But we still require that amount of voltage, and that's what we're measuring. That's why we're seeing about 0.7 volts lost across our diode. That's the amount of pressure it requires to keep the valve open, and that pressure is used up, if you like. The water pressure coming out is a little bit lower than going in, and that's what that 0.7 volts is, okay? And this has a name as well, and this is called the forward bias voltage. It's the amount of voltage you have to apply before the valve opens, before you counteract the spring, okay? What about the reverse direction? Do you think the diode will continue to pass no current infinitely, no matter how much voltage we put across here? Well, the answer actually, and not really surprisingly, is no. You will reach a point at which the diode can no longer resist the pressure. It's like the valve breaking in the pipe, okay? And at some point, the diode will conduct and current will flow in that direction. This also has a name. Everything has names, yeah. This is called the reverse breakdown voltage. The reverse breakdown voltage will depend on the type of diode, the specification for the diode. Some diodes are made to withstand more voltage than others. This forward bias voltage will also depend on the type of diode. But as I mentioned originally, there are a number of different types of diodes for different purposes. This voltage is much more related to the type of diode. And those types, for example, could be a silicon rectifier diode like the one I have here. It can be something called a Schottky diode, and we'll talk about all these in the next video. It could be a light emitting diode of various colours. And this voltage is basically related to the type of diode it is. This one is related to the rating for this diode. So you can have, as I mentioned, silicon rectifier diode. That's the type I've been using to demonstrate on this video, by the way. And all silicon rectifier diodes will basically have the same forward bias voltage because of what they are, silicon rectifiers. But the reverse voltage can be vastly different depending on the actual model. It could be tens of volts, it could be thousands of volts. So from this now, we can actually understand how diodes are rated. What ratings do you see if you look at the data sheet for the diode, and what does it tell us about the diode? So the important ratings that specify a diode are the maximum current. So the maximum current is effectively how much current you can pass through the diode before it fails, before it burns up. As we showed earlier in this video, the diode I was using was rated at 1 amp, and I was actually passing 5 amps through that diode. And for a short period of time it can handle that, but it just burnt up. The larger big fat diode I was showing you was a 6 amp diode, so that would handle the 5 amps. It's rated to be able to handle that current. Remember, the power supply itself was limited to 5 amps. It wouldn't give an infinite current. The other rating for a diode is the voltage. But this voltage is in actual fact the reverse breakdown voltage, not the forward bias. And the reverse breakdown voltage can be tens of volts, 50 volts, 100, 200. The one I was actually testing, this one was actually 1000 volt diode, and funny enough, actually the 6 amp one I also showed you was 1000 volt, but the very small glass one I showed you was 50 volts. So those are really the two ratings you'll see on the diode on the datasheet. The maximum reverse voltage it can withstand, the reverse breakdown voltage. It doesn't mean it has to have that voltage to work. That's just the maximum it can withstand before it fails. And again, the current, which is the maximum current you can pass through it before it fails. It doesn't have to pass that current to work. It's just the maximum it can pass. There's actually a number of other factors that come into diodes which are of less importance, but one I will mention, and that is the speed of the diode, without using too much of a technical term. How fast can the diode switch on or switch off? Because this is not actually instant. It will take a certain amount of time, probably microseconds or nanoseconds, a very short amount of time, but still a finite amount of time for the diode to go from non-conducting to conducting. And once it is conducting, it takes a finite amount of time to stop conducting again. Like the analogy in the valve, it can't just go from open to closed, it has to move between the two. And the same applies to our diode. So the speed, the switching speed we'll call it, is also an important factor in some cases. The higher the frequency signal, AC, that's going through the diode, the more important this becomes. But for now, just be aware of it. Okay, so I think that's enough for this video. I did mention there are a lot of different types of diode that have different forward bias voltages and also have other properties which are different. So in the next video, let's look at all the common types of diode we're likely to come across, and maybe some of the rather less common ones as well. And we can look at what makes those diodes special or different. Is it a different forward voltage bias? Is it a faster switching speed? The reverse breakdown voltage, what makes these diodes different and why are they used in other applications? And no doubt a few other factors as well. Okay, I hope you enjoyed that, and I look forward to seeing you all soon on another Learning Electronics Repair video. Ciao for now, guys.